And now, I want to introduce our first speaker and the topic he's talking about. iOS kernel exploitation archaeology. A kernel exploit from late 2013, early 2014 will be digged out and analyzed proper archaeology. All the digging and analysis is done by RHP, here to my left on the stage. And give him a big round of applause, and the stage is yours.
Thanks for the introduction. Okay, first of all, thank you all for being here. As the person that did the introduction told you, this is going to be an archaeology talk, so I apologize in advance if it's not that interesting to you. So we'll talk about a bit older stuff rather than new things. Okay, so a few things about myself. Actually, I think from all these things, the most important are the FRAC papers, right? So yeah, so yeah, let's ignore all the other stuff. Okay, so what I'm going to talk about, I'm going to talk about the Evasion 7 kernel exploit. Now, Evasion 7 was a jailbreak. It was released by the evaders on the 22nd of December 2013. It supported iOS 7 to iOS 7.1 beta 3. That's not the 7.1 stable release, right? So that's a beta. And it supported all devices at that time, including the iPhone 5S, which was the first 64-bit device, except the Apple TV. So I decided to reverse engineer the kernel exploit of the jailbreak to focus just on that, because I was really interested not so much in the bug itself, which was, as we will see, not very complicated, but I was really interested to understand the exploitation techniques that the evaders used. So I started reversing it and I understanding it, and at some point I just said I'm just going to do a re-implementation of the kernel exploit. So this talk is basically my notes on this whole process, and of course it's not a jailbreak walkthrough, right? And I'm going to specifically focus on the various problems I encountered during this task and how I overcome them. And hopefully it's going to give you some helpful takeaways for if you do iOS kernel research nowadays. Okay, so the general outline is I'm going to say a few things about Evasion 7 to set up the stage, and then I'm going to explain the kernel bug itself, and then I'm going to talk in length about my debugging setup, and I think that's a very important step that usually phone or embedded talks, exploitation talks don't analyze that much, and I think it's a really important part. Because usually having a working debugging setup is basically maybe half the job of doing a reliable exploit. Then I'm going to talk about my implementation of the exploit, and hopefully at the end we're going to have some things to take away, or maybe not. We'll see. Okay, so it was the Evasion 7 jailbreak was released about 4 years ago. And that's the archaeology in the title. That's ancient history, right? And if you were following the jailbreak community, you might remember this huge drama around this jailbreak. Initially with Geohot, and if he was planning or not to release it before the evaders, and who he was planning to sell it to, and some leaked discussion that he had with someone that he was offering money to buy, and Geohot, his jailbreak was supposedly using some of the bugs the evaders were using. So this huge drama. And then after the Evasion 7 jailbreak released, like maybe a few hours ago, people realized that if your phone had a Chinese locale, then the jailbreak was installing a piracy app. So that was basically a third-party app that was taking you to an app store not operated by Apple, but by Tig, that had some pirated versions of the real applications on the App Store. And of course, that also created like a huge drama, this practice. Okay, so a lot of things were said about that jailbreak at that time and about the Tig piracy App Store, but what I really set apart was this tweet. And the really important thing that I liked about this tweet is that it doesn't really make sense. So he says that we have to decide to remotely disable the default installation of Tig in China for further investigations on the piracy. So that whole thing doesn't make sense. So you mean you didn't know what was happening? You didn't bundle it with a jailbreak? Are you going to disable it for new installations? And then what does remotely then mean exactly? So what about the people that already had the apps, the piracy app? How are you going to disable that? Is that what remotely refers to? So that's an excellent tweet, I think. Okay, so some point after the version 7 jailbreak was released, Jeho did a write-up on the userland part of it. So he analyzed how the userland part worked, and he stopped at the point of gaining root. And basically, he mentioned in his write-up that the Evasion 7 untethered binary, which is basically what was doing the kernel exploit, was obfuscated. And as we will see, this was indeed the case. And as far as I know, that's the first jailbreak that used deliberate obfuscation. I don't know the reason. I assume it's partly to hide the piracy app store that was bundled with it, and maybe partly to hide the bug, the kernel bug. But I'm not sure about the reason. Now, POSIX Ninja, who found, as far as I know, the kernel bug, did a write-up on the kernel bug. It's on the iPhone wiki, and he basically describes the bug, and he stops at the point where he gets a crash log from GDB. So he doesn't say anything about how to exploit it. Okay, so after all these things happened, then I decided to reverse engineer the untethered binary and understand the exploitation techniques. And I was really interested to reverse engineer the obfuscation that the evaders were using. It seemed like an interesting challenge. But as I also mentioned earlier, I was really interested to understand the exploitation techniques that they were using. That was more important for me at that time. And okay, so the jailbreak was released December 2013, and I started doing that around February 2014. And I did that while having an actual day job, right? So I was spending at most 2 days per week on that. So what was my setup? I had an iPhone 4, and if you know about iPhone 4s, they have a boot ROM bug called LimeRain, which basically allows you to load arbitrary kernels, unsigned kernels, on the device and run them, and that basically means that you can very easily set up kernel debugging. So initially, I had an iPhone 4 device with iOS 7.0.6. I want to remind you that iPhone 4 is ARM32, right? I also had an iPhone 5S with the same version of iOS, and I had that in order to verify all my findings and all my tests on, to redo my tests on an ARM64 device. And as I told you, the iPhone 5S at that time was the only ARM64 device, actually, I think, on the market. I don't think there was another consumer device with ARM64 at that time. So that's the exact version of version 7 I was analyzing. And of course, ZDAT, ZDB, LLDB. Now, the lols in this slide, they don't actually refer to something funny. They actually mean something very painful, and that caused a lot of sleepless nights. But I'll get on to that. Okay, a few things about the obfuscation. So not all of the functions of the untethered binary were obfuscated, but some of the important ones were. And those were the ones that were triggering the bug, and they were actually doing heap manipulation and all the other important things. Now, I have been told, I haven't checked that, but I have been told that later versions remove the obfuscation, but I'm not sure about that. I haven't verified it. And I already had my implementation done at that point, so I wasn't that interested to look at that. So, as I mentioned, the kernel bug that the Evasion 7 untethered binary was based on was found by POSIX Ninja. And basically, as far as he says on that iPhone wiki page, he used that 6-line bash script fuzzer to find it. So as you can see, he basically creates device nodes and with controlled arguments here, like minor and major numbers. Now, in order to get to the point to create device nodes, you basically need to be outside of the application sandbox that exists on iOS, and you also need root privileges. And that's what I refer to as the userland part of the Evasion 7 binary, and I'm not going to cover that at all. So I'm going to start my analysis from the point on that we have escaped the sandbox, we have obtained root, and now we go to exploit the kernel bug. Now, that's code from that version of the XNU kernel that had the bug. Now, this PTSD open function is called every time userland code opens a dev-ptmx device. And then this ptmx get-ioctl function is called. Now, the important thing here is that dev here is completely user-controlled, and then it's passed to this ptmx get-ioctl function with no checks at all, right? And then this ptmx get-ioctl function uses this to index an array without any checks. So basically, the bug is an invalid indexing bug, right? So since you can control that, you can put here whatever. I have here the ptmx ioctl struct. Okay, this array here is, so this state struct here is global to the kernel, and this piece ioctl list array here is on the kernel heap. And it is an array of ptmx ioctl structs. And that's the ptmx ioctl struct. And the important thing here is that I'm going to refer to again and again during the talk is that it has a pointer to a tty struct as the first element of the structure. Okay, so we control the index to the array. So what can we do with that? So here, as you can see, the ptmx get-ioctl function returns whatever it indexes, right? So as you can see here, it assigns it to this PTI variable and then does all kinds of interesting things. So PTI is controllable, TP is controllable here as well after this dereference here to some controllable value. And I mean, in other code paths of the kernel, this is called again. And so there are a lot of things to consider when you know the bug and then you try to think how to exploit it. Okay, one important thing here that I wanted to mention is that this ptmx, this function here, ptmx get-ioctl, also does the allocation of this struct here, of this tty struct here. And that's important because I'm going to use it further on. Okay, another important thing is that you basically, this bug, what allows you to do is you can control the size of this array here. So by, can you see that? Okay, so by repeatedly open the dev-ptmx device, you can grow this array. And you can grow it, as you see here, by this grow vector. That's 16, but it doesn't matter. What matters is that the size of this array in bytes is controllable by you, the person who are trying to exploit this bug. Now, for example, these are nodes from my exploit. So if I did one allocation, if I did one open of this dev.ptmx device, then this array was going into calloc 64. If I was doing 17, it was going to calloc 128. If I was doing 33 opens here, it was going to calloc 192, and so on and so forth. So I could decide in which calloc zone I could place the array. If you don't know calloc zones, they're basically, you can think them as you can think calloc zones as containers for heap objects on the kernel heap. All of them can be of different type, but all of them are of the same size, right? So calloc 64 can have different structures of size 64 bytes, but all of them are size 64 bytes. Okay, so I started debugging the untethered binary in userland. That's how I started. So initially I was using GDB, and I found out that nothing worked with GDB. It was, at that point, Apple was starting to move from GDB to LLDB. So I don't know, maybe that was the reason GDB wasn't tested. It wasn't tested at all. So when I say nothing worked, I mean that I was placing breakpoints and they weren't hitting, and I was trying like stepping, and it was continuing execution and stuff like that. Sometimes I couldn't even attach to the binary. So then I moved to LLDB, to an LLDB setup with debug server, and things were much better. Now, while I was experimenting still from just with userland debugging, my iPhone 4 device went into a recovery loop, and I wasn't able to get out of it. So I was forced to do a clean restore of the device. The problem was that at that time, only iOS 7.1 was signed by Apple. So I couldn't install a version of iOS that had the kernel that had the bug that I was interested to look at. But on the other hand, I couldn't not restore my device because that was the only device I had at the point that I could do kernel debugging with. So I upgraded my device to 7.1. As I just told you, 7.1 didn't have a vulnerable kernel to this bug. So what I wanted to do was basically to boot an iOS 7.1 device with a 7.0.6 kernel. And in order to do that, I could use the limerain bug that allowed me to boot arbitrary kernels. And the utility to do that was Red Snow, right? The problem was that Red Snow only supported up to iOS 6. And it didn't have support for iOS 7. So I left all the other things I was doing, and I started reversing Red Snow to understand how it worked. Red Snow, if you don't know, it was back then and it still is closed source, right? So I started reversing that to understand how it worked in order to support, for me to to patch it, to binary patch it to add support for iOS 7. And I spent like, I don't know, maybe a month on that. And then I realized that it wasn't leading me anywhere. I couldn't understand a lot of things about how Red Snow was implemented, so I stopped doing that. And at that point, I found OpenSnow, which was an effort by WinOCM to re-implement Red Snow as open source. So it seemed to have support for iOS 7, and that was good. I tested that, and it was working. Now my problem was that I couldn't have an arbitrary length of boot args. Boot args are the arguments that you pass to the kernel when it boots, and they are really important in iOS because by passing certain boot args to the kernel, you can disable signing checks, you can enable kernel debugging, so it's really important to be able to pass arbitrary length boot args. And iOS 7.1 was using up to 39 characters, so that was the reason OpenSnow couldn't support more. So what I ended up doing was I patched IBEC, which is basically the loader of the kernel, right, that passes boot args to the kernel when it boots. And basically I changed the pointer to the boot args to some other place that had much more space. So at that point, I was able to pass arbitrary length boot args to my kernel. So where we are at last. So I had an iPhone 4 device with iOS 7.1, and I was using OpenSnow to boot the 7.0.6 kernel that had the bug that I was interested to exploit. Now, one side note here is that as I was doing that and I was trying to add to OpenSnow all the patches to the kernel to enable kernel debugging, I was reversing the evasion 7 binary as well. Now, the evasion 7 binary was trying also to, after it exploited the kernel, it was patching it to enable kernel debugging. But so I was just copying their patches, right, and adding them to OpenSnow. But I realized at some point that they missed some checkoff for the debug-enabled variable, and KDB wasn't really working. So the session was established, and it seemed like it was working. But if you try to actually use the kernel, the KDB, the kernel debugging setup to do actual, like to attach the debugger to the kernel and do whatever, like place a breakpoint or step, then KDB just froze. So I added another patch that was required on that. Okay, so kernel debugging at last, but that's not really what happened, because breakpoints didn't always work. So you were placing a breakpoint and it wasn't hitting when execution was reaching there, and you were trying to step instructions and the execution just continues. So you were stepping one instruction, it was just like you were typing continue. And if you were taking too long to type lnlldb command, then KDB froze, and then you had to restart your device, reestablish the kernel debugging session, and start from zero. And if you issue commands too fast, then KDB froze again. So you have to reboot again. It was amazing. It was a great time. And now I did similar stuff with iOS 6, and I distinctly remember that it was much easier and kernel debugging worked much better. And I mean, the issue that comes to everyone's mind that does that is, do Apple engineers really use KDB for debugging the iOS kernel, or do they use something else? Okay, so now I could debug the evasion 7 untethered binary both from the userland side and from the kernel side. And that was good because I was analyzing at runtime, and at the same time I was reversing it in NIDA. So the obfuscation, I could do it much faster since I was taking hits from runtime. So at that point, things started moving fast, and I quickly found that it was abusing the DTY structure to obtain read-write access to physical memory. I mean, that was interesting to me, but I was expecting something else. I was expecting something like what they did in iOS in the version 6 jailbreak, that they did like a lot of heap manipulation, and that's my interest actually, heap exploitation. So at that point, I decided to stop reversing it and re-implement the exploit the way that I wanted to do it. So obviously that wasn't work from scratch. It was from everything that I understood up to that point. And what I really wanted to use was the VMAP copy structures technique by Dowd and Mant. And I'm going to explain that in the following slides, how it works. Okay, so at that point, I had a clear understanding of the bug, of what it was, and I had a general idea about how to exploit it. And I mean, if you've done that, then it takes a lot of pen and paper, like ideas you develop on paper, then you go test them, and they don't work, and then you design them again, and and you fail, and you despair, and then you suddenly have an idea, and you spend I don't know, like 2 nights, you stay up until 5 in the morning testing things, and they don't work, and then you despair again, and ad nauseum. But eventually you get somewhere. So let's talk about exploitation now. Now, a few things to refresh your memory about the bug. So as I said, it was an invalid indexing bug. This PICIOCTL list array was on the heap, and I could control in which calloc zone it can go. I can grow it, but once I grow it, I cannot shrink it back. Now, that's code from that ptmx get IOCTL function. So basically what it does, it allocates a new ptmx IOCTL structure, and then it uses the index that you provide, that you control to store the address on the array. Now, this allocation here, this struct here, goes into calloc 88, and that's useful for the next parts. Okay, a few things about the technique I wanted to use, about the exploitation technique I wanted to use. So it's the VMAP copy technique. It was proposed by Dowd and Mudd, and basically they were spraying the heap with these structs here, the VMAP copy structs, and assuming you have like some way to corrupt this struct that you have sprayed on the heap, if you can override this kdata element here, then basically what you have is leak of kernel memory, either adjacent, like next to the kdata, whatever is below or above the kdata pointer, or arbitrary if you put whatever address you want in there. By overwriting the calloc size element here, and then freeing the struct on the heap, you put it on a wrong zone, and basically when you allocate it back, since you put it on a different sized zone, you can have a heap overflow. So that's a general overview of this technique. So you corrupt this struct and you get exploitation primitives. Okay, so what was the idea I had at that point? The idea was to use this piece IOCTL list index bug to corrupt this kdata pointer here, and to have relative leak of kernel heap memory. And that would be my first step towards exploiting the bug. Of course, the end goal is to have arbitrary read-write, right? And of course, it was just a fuzzy idea at that point, and that's always the goal, but when you study the bug and you see the different code paths and how the things you affect are used, then you have some maybe not completely concrete things in your mind, but you know that interesting things can happen. So that's what I had at that point. Okay, so let's talk about the exploitation stages now. So at stage 1, I sprayed the kernel heap with VMAP copy structs, and I decided to work on the calloc 256 zone. And the reason for that was completely arbitrary, was because of all the kernel debugging I have done up to this point of this untethered binary, I saw that this calloc zone was not really used that much, either by the kernel or by whatever the exploit was doing. So that's good, because it means that you as an exploiter can have much better control over the kernel heap if there aren't other things placing allocations on the zone you work. So I decided to use the calloc 256 zone. I avoided, of course, calloc 384 because the TTY structs were going there, and that would really mess up my heap arrangements. So the first, let me actually. Okay, so what I wanted to do was to do this. So initially, you spray the heap with VMAP copy structs, and you control both their size and their contents. The contents don't matter at this point, so just their size matters. So I spray with 256 bytes VMAP copy structs, and then I free every other second one, and I create this kind of pattern, like a VMAP copy and a free slot, and VMAP copy and a free slot. And then I grow the PSIOCTL list array to 256 bytes, and then it goes into one of these free slots here. Now, the code for doing that looks something like that. So what this basically does is sends, it creates this, so if you see here, the out-of-line MAC messages as basically these VMAP copy structs. And their size is 256, their buffer doesn't matter at this point, and you just send them like Mach send message. And then after I have sprayed with them, then you free every second one here with this loop here. So in order to make these free slots, you just receive this MAC out-of-line messages that correspond to the VMAP copy structs. And after you've created the holes, you basically grow the array to 256 bytes. How do you do that? As I mentioned earlier, you open the devptmx device a number of times. How many times? It doesn't matter, like a specific number of times that I mentioned earlier, that I have noticed grows it to 256 bytes. So that's the arrangement you have at that first stage. Okay, so the second stage is done on the calloc88 zone. So I spray again with VMAP copy structs, and this time I make them 88 bytes to go to the calloc88 zone, and then I create again holes. And then I trigger the bug with the invalid index value. And remember that when you trigger the bug, a PTMX IOCTL struct is allocated, and this goes to calloc88. But because on calloc88 I have created this pattern of used free, it goes into one of the free slots. So now I have a PTMX IOCTL struct into one of my free slots. I don't know where that is, but I know that it falls into the pattern, right? So I trigger the bug, and remember that basically you control this index, right? So since I control the index, I point it to the VMAP, to the key data element of the VMAP copy struct that I know is below the free slot that the array went into. I don't know the address, right? I can put like an address there, but I know the relative distance in bytes because I created the pattern, the heap pattern. So let's go to, okay, so it looks like that. So that's my first stage, right? Free VMAP copy. And this is the same pattern on the calloc88 zone. When you trigger the bug, this PTMX IOCTL structure is allocated. It goes into one of the free slots, right? And then the bug itself, which is what we see here, is, remember, you control the index. So this is the new allocation that went here. And then it goes and stores this address where the index tells it to store it. But remember that this is controlled, we control that. So what I do, I point this here relatively to the neighboring VMAP copy struct at the kdata field, right? So in this kdata field here of the VMAP copy struct, I have now this address, right? So that's how the heap looks like. I have here the code. It's very similar to the first stage, right? You spray with VMAP copy structs of size 88, max and message, right? And then you receive every second one. You create the holes on the 88 zone, and then you trigger the bug here, right? This invalid piece index number here is basically what points relatively to here, right? So I have now the address of this PTMX IOCTL struct, which is an address on the calloc88 zone. I have it on the kdata field of this VMAP copy struct here. So what I do, I can simply receive this message, and in its content, I can see the address of that slot on the calloc88 zone. So that's the code to do that. I simply receive all the messages, and that's my address. Okay, so at this point, what I only have is this address here, right? I have the address of this heap slot. So at that point, I started looking at other code paths that this invalid index, what other variables this invalid index was influencing. And I found a code path that was actually was giving me a write. But in order to reach that, I needed to survive several dereferences. And what I only knew was just the cal.88 address, right? Nothing else. So I will now walk you through everything that gave me this right. So I clean up the calloc 256 zone, and I spray it again with VMAP copy structs and create holes, exactly like the previous step, the first stage. Again, next to the IOCTL list array, I have a VMAP copy struct, but at this time, in all the VMAP copy structs, I put a payload of this fake PTMX IOCTL address I have. And remember that the first element of the PTMX IOCTL struct is a pointer to a TTY struct. And I can use the leaked address I have for this pointer that I didn't know where to point it to. So the next step was to clean up the cal.88 zone and spray it again. And again, I sprayed with VMAP copy structs. But at this time, at the payload, I can put now the fake TTY struct that the PTMX IOCTL struct is pointing to. The problem at that point was that the TTY struct was 256 bytes, and cal.88 has the slots are only 88 bytes. So I couldn't just with the elements of just with the first 88 byte elements, I couldn't get to the path that was giving the write. So I needed to find some other way to host my fake TTY struct. So remember that I couldn't work on any other calloc zone or anywhere else because what I only knew was the address of that cal.88 zone. I had nothing else to build on. So at that point, I started doing a much more complicated heap arrangement. So instead of spraying just one thing, I was trying to create a pattern of two controlled things. Now, I couldn't use VMAP copy structs for both these slots because the VMAP copy structs has a header, right? So it would mess up my fake TTY struct. So by reading Ionic's kernel heap exploitation slides, I realized that I could spray the heap with XML properties of length 88 from that Apple JPEG driver. And I could place as a second control object after the VMAP copy struct these XML properties, which are completely controlled in content, and I could host the second part of the TTY struct there. I mean, it's still not 256 bytes, but what it gives me is the ability to survive all the references to reach the write that I was interested in. Okay, so a few things about the TTY struct. So that's what I wanted to create on the cal.88 zone, right? So that's the TTY struct that the PTMX IOCTL struct is pointing to. Now, what basically I wanted to do here is I wanted to point, the final thing was to use this C-list struct to control this element here, C_CS, as the start of the ring buffer for the TTY to give me an arbitrary write. To give me a controlled write. I started playing a bit to use it to do arbitrary write, but I found that I wasn't able to do it because at a later stage, some other parts of the TTY struct were needed that I wasn't able to control, so I only had two 88 slots to host my fake TTY struct. So that wasn't stable, so I was only using that to do a relative write. So we'll see the code later on. Let's go to the heap layout. So that's the third stage. Again, remember, I spread the calloc 256 zone with VMAP copy structs freeze just to place my PSIOCTL list array next to VMAP copy struct. Remember that I control the contents of VMAP copy, right? So I placed in the buffer of VMAP copy this PTMX IOCTL address that I know, and I point the invalid index that I control to this PTMX IOCTL, this address that I put here. And what is this address? Is that leaked address that I got in the previous stage, which points to the calloc 88 zone. And what's the arrangement of that calloc 88 zone? Is, as I told you, a VMAP copy followed by an XML properties. VMAP copy, XML properties. And all these hosts this fake TTY structs, right? All these are the same. I just explained here how it looks like. So this points to the kdata element here, and the rest of it holds the rest of the, all this is basically the fake TTY struct, like the buffer of the VMAP copy and then following the XML contents of this heap allocation. And where do I, this C underscore CS pointer that I told you that I wanted to control, where do I point it? I point it relatively, again, I don't know any addresses, but I can point it relatively since I know since I created this heap arrangement, I can point it relatively to the size or the calloc size of the neighboring VMAP copy struct. And why do I need this? Because I want to use the VMAP copy technique by Mark and Dode that I mentioned earlier. So that's the end goal. So what the code looks like. Okay, that's the spray of 256. We have seen that a lot of times. Then we have the freeze. Wait, no, that's not the freeze. So that's the allocations of the 256. That's, yeah, I don't have the freeze here because they don't matter, because we have seen them before. So what I have here is the spray of the calloc 88 zone. And the important thing here is that what I wanted to show you is that at every step, I took two allocations. One is the VMAP copy struct here, with the max send message, and the second part is the XML properties, which are sprayed on the heap when you open the device driver, the Apple JBack driver. And what are the contents of that XML properties? They're basically that the second part of the fake TTY struct that have the controlled C underscore CS pointer that will give me the relative right. So if you see here, I have this function setup fake TTY that basically creates the structs since I don't have to type all the time. And we are at second stage here. And basically what you can see here is the creation of the fake TTY struct, right? So that's the different elements of the fake TTY as we saw it from the code. And that's the right offset I wanted to, that I pointed to the kdata field of the neighboring VMAP copy struct. So again, that's how it looks like in the heap. Okay, so after that, after we have arranged we have arranged it this way, we trigger again the invalid index array bug, but at this time on a slave PTMX device. I was only doing that on a master PTMX device, but in order to reach that right code path that I mentioned, you need to do it on a slave PTMX device. So that's what happens here. And then you simply write to the corresponding descriptor, and it just dereferences this C underscore CS that you controlled, and it writes to it whatever you want to write. And what do I want to write? I want to write a new size for the VMAP copy struct for the calloc size field of the neighboring VMAP copy struct, so I can use the DAUT and MAD technique. So putting everything together, so at that point I have a controlled corruption of a VMAP copy struct, and I can use the primitives to get an arbitrary leak. So I can leak, for example, the KSLR slide, and I can do a heap overflow. Again, these are how you can use the primitives that Mark and Dowd gave us. Now, I also know my location on the kernel heap, and remember that's basically we found that on the first two stages, and we use only that, like where that PTMX IOCTL struct was stored on the kernel heap. That's the only thing we knew, that address, in order to successively build on it, in order to reach like a much more useful primitive. And the interesting thing here is that everything up to this point is data only, right? So you haven't injected any code, you haven't done anything at all that you could be caught somehow by a kernel self-protection mechanism or this kind of things. Everything is data only. So once you reach that point, how do you get PC control? So since you can use Dodge and Match technique, you can basically do a heap overflow. So you can again do a heap arrangement. You can place IOKit objects next to VMAP copy structs where you can overflow from, and you can corrupt IOKit objects. And from there you can have also you can do an arbitrary read, right? So you can, by the arbitrary read, you can read the vtable of the IOKit object, so you know the KSLR slide, and you can corrupt it in order to get PC control. And of course, getting to a whole JBLIC from that point is out of the scope of the stock, but it's not that hard actually from that point on. Okay, so after doing all that, how close was that exploit to the real evasion 7 kernel exploit? I'd say it was pretty far off, but I mean, it wasn't my point to recreate it like completely, but it was my point to play with the heap and to try to do complex heap arrangements and to see how much I understand the iOS kernel heap. That was the point of this whole exercise for me. Okay, so some lessons learned. So the real surprising thing for me at that point was that I couldn't believe that Apple does kernel debugging via KDP. It was very flaky, it was very unstable. As I told you, if you type commands too fast, it froze. If you type commands very slow, it had like a watchdog timer and it froze, I think. It had a watchdog timer or something like that. And I couldn't believe that Apple engineers were using this interface to do kernel debugging. So it was really hard to do anything on the kernel side of iDevices. But of course, I don't really mean that you shouldn't mess with these things, right? I mean, these devices are really interesting, and it's really becoming harder to hack them. But I think it's much more fun. And I think the only takeaway maybe is that you shouldn't report bugs to Apple at all. And if you need street cred, you should just report white elephant bugs to them. I mean, that's always good. And I mean, this is getting very esoteric, right? There are not a lot of information, and Apple keeps changing stuff, and everything is closed source. I mean, all the important parts are closed source. And I mean, I really think people that work on that thing should share notes as much as possible. Okay, so these are some of the people I was talking to while doing all this, and I want to mention them. And basically, that's all of the material I have, and I'm open to any questions you might have.
Thank you, ArcP, for the talk. So we have prepared microphones 1, 2, 3, and 4 in the room, and we have a signal angel. I think you, when you have questions, you can give me a hand sign. But I think we start with microphone 2 here in the front, and please ask questions and no comments. There's time after the talk.
Okay.
Go ahead.
Thanks for an awesome talk.
Thanks.
I have a question about heap spraying. Was your heap spraying really stable? If it is not successful, did it crash the device?
Yeah. So I haven't mentioned it here, but it was pretty stable. I think it was something like, because I did a lot of tests for that, because it was really interesting for me to know. It was maybe something like 90%. So nine out of 10 times it worked. But if it didn't work, yeah, yes, it crashed the kernel and crashed the device. Yeah.
And did you try to return heap into some kind of initial state to start your exploit from scratch?
Yeah, that's true. I haven't included that, but you're right. So the initial step on every spray that I mentioned here was to spray a lot of objects of the specific size you were targeting in order to get basically a new page of the calloc zone, right? So so even if, as I told you, the calloc 256 zone wasn't that busy, there were still allocations going on it, right? So if you did a lot of initial spraying, you were making sure that when the allocations that mattered to you were made, were on a new page that wasn't too much noise from other allocations from the kernel. So yeah, you're right. I haven't included that, but yeah, that happened.
Thanks.
Okay.
Great.
Thanks.
Then microphone 1, please.
Also, thank you for your awesome talk again.
Thanks.
My question was, nowadays it's way harder to use VM copy. I think Apple truly deprecated it.
Yeah.
It's not possible anymore due to security. Do you see hope in reconstructing some function that does the same, or is it totally dead now?
Oh, you mean the VMAP copy technique?
Yes.
No, I think it's completely dead now.
All right. And I recently saw on the iOS logs of vulnerabilities that again vulnerability in Apple JPEG driver was found. Do you think, have you looked into it, or?
Well, the Apple JPEG driver is one of the 4, I think, IOKit drivers that you can reach from the container sandbox, right? So that means it's very, very fast by everyone, Apple included, and very audited. So I'm not saying that there aren't things there, like interesting findings,
Okay.
but if there are, they're not going to live much longer, I think.
Okay, thank you.
Thanks for your question. And now from the Signal Angel, question from the internet.
Yes, I have a question from the internet. How long did this research take you? You said 2 weeks in the beginning, but from begin to end? How many hours about? Because you also said it was during work.
No, it didn't take 2 weeks, no. It took like maybe close to 3 months, so 2 months and something like that. So I spent, as I mentioned, I spent like a complete month, I think, like maybe 3 weeks, maybe not a complete month, just on reversing red snow and trying to get red snow to play with iOS 7. So I wouldn't count this month in the exploit part of it, right? So if you're interested just in the kernel exploit part, I would say something like maybe 7 weeks, something like that. But just with two, maybe 3 days per week, right? Not complete weeks.
Okay, then microphone 1, please.
Congratulations, your talk. It was really interesting. I liked it a lot. And my question is, if the technique you use to exploit the bug, it works in FreeBSD or any other BSD as well?
Oh, no. I mean, the VMAP copy struct doesn't exist anywhere else except the XNU kernel. But I think the interesting takeaway is that you can do complex heap arrangements if you understand the kernel heap allocator, right? So this process I described by creating holes and maybe controlling 2 allocations in order to host fake structures that you are able then to use to get exploitation primitives, then that's applicable everywhere, right?
Thank you.
Okay, then we go to microphone 2 again, please.
So I saw one sentence, just not report, or just don't report the bugs. I would like to understand your thinking behind, because I think this is really important for companies to know the bugs that they made and make the products better. And this is really beneficial for researcher because, for example, Apple, they pay a lot of money for the bugs.
Okay, yeah, I don't have much to say on that. I mean, apart from if all the bugs are fixed, then you won't be able to do this kind of work, and it's not fun. So I don't have anything else to say on that. Sorry, I don't have anything else. No comment.
Okay, Signal Angel, do we have another question from the internet? Okay, then please a big round of applause for our speaker.
Thanks.